Fine. ಆಯ್ತಲ್ವಾ? ಓಕೆ, ಶೋರ್. ಡೈರೆಕ್ಟ್ ಸ್ಟಾರ್ಟ್ ಅಲ್ಲ? ಈಗ ಆನ್ ಇದೆ ಈಗ. Hello all. Today we are going to discuss on mathematical background for cryptography. In this one, we are covering the concepts of congruence and algebraic structures. Agenda for discussion is congruence. Then after that, we cover useful algebraic structures, namely groups, rings, and fields. Learning objectives. After attending this session, you shall be able to explain the meaning of congruence, describe useful algebraic structures and their properties, namely groups, rings, and fields. First, we shall discuss on understanding congruence. Earlier, we had seen the importance of modulo operator. Whenever we make use of the division, then two inputs as operands are given, then division gives out two outputs, Q and R, quotient and remainder. In modulo operator, we are only interested in the non-negative remainder value. This non-negative remainder value plays very crucial role in our cryptography. Now we shall discuss on concepts that facilitate understanding of congruence. We shall look at set of integers, then set of residues. Set of integers. This is usually denoted by capital Z. It contains all integral numbers with no fraction from negative infinity to positive infinity. We define the set of integers as Z equal to opening flower bracket, then minus infinity up to plus infinity. Now, whenever we carry out division, from the division, we are going to establish a set of residues, which is represented as Zn. The result of the modulo operator R, please you can notice here the symbol. We have got three lines here, not equal sign, which represents congruence operation. R equal to congruence of D mod n is always a non-negative integer between 0 and n minus 1, that is 0 up to n minus 1 values the R is going to have. R is a remainder. The modulo operation creates a set of least residues of modulo n or Zn. This understanding of the concept Zn is very crucial. We shall go deeper into it now. However, we need to remember that although we have only one set of integers z, we have infinite instances of the set of residues Zn, one for each value of n. What does it represent? So we shall just try to understand what we had just mentioned. Set of residues and instances of set of residues. That is what we shall understand now. Although we have only one set of integers z, we have infinite instances of the set of residues Zn, one for each value of n. Example, following figure shows the set Zn. Based on what value we give to n, we are going to create the set Zn. Now, if the n value is 3, then all the values between 0 and 3 will be listed out under Z3. If you look at it here, Z3 is going to have 0, 1 and 2. For Z5, we are having set of residue values as 0, 1, 2, 3, 4. Similarly, Z7 is having 0, 1, 2, 3, 4, 5, 6. Z9 is having 0, 1, 2, 3, 4, 5, 6, 7, 8. In cryptography, we often use the concept of congruence instead of equality. Mapping from set of integers z to set of residues is not one-to-one, but it is infinite numbers of z can map to one member of Zn. Example, the result of 2 mod 10 is equal to 2, 12 mod 10 is 2, 22 mod 10 is 2. Now we can see member of z integers set is 2 here. And for getting this particular residue, we carry out mod operation on 3 values, that is 2, then 12 and 22, which are members of z or set of integers. So all these 2, 12, 10, when we perform the activities of mod 10, belong to residue 2. Means 2 mod 10 also resulted in a residue, 12 mod 10 also resulted in residue 2, 22 mod 10 also actually resulted in residue 2. Means many values of z, which is the set of integers, map to one value of Zn, that is set of residues. That is 2, 12, 10 are mapped to 2 of Zn here. We call 2, 12, 10 as congruent of module 10. Means they are producing and mapped to the same value of residue. Now to understand congruence, we have to be very clear about certain notations and ideas. First important and foremost thing is that we have to understand the difference between equal to and congruence operators. Equal to is having 2 strokes, whereas congruence operator is having 3 strokes. We have to very carefully look at these differences. Now, equality to operator maps a member of Z to itself. Means when we make use of the operator and apply it on operands, for example, let us say 2 plus 3, then what value we get is 5. This 5 also belongs to the integer set. 5 minus 7. At that time, we get minus 2, and we have to convert based on what module value we are making use of, and consider the positive value in the set of integers. Like that, we take 2 operands from the set of integers Z, carry out an operation on it, and what result we are going to get is also an integer, belongs to the Z set only. However, in case of congruence operator, we are mapping many members from Z, not to Z itself, but to a member of set of residuals Zn. So the first difference is we are not mapping back to Z as we did in the equality operations, but in congruent operations, we are mapping the set of integers to a member of set of residues. Second and foremost difference between equality and congruence operators is that equality operator is one-to-one. Means when we carry out the activities, what output we are going to get is going to be unique based on the uniqueness of 2 inputs we are considering. However, in case of congruence operator, it many to 1. This thing we had seen it earlier, that is making use of 2 mod 10, 12 mod 10, 22 mod 10, all had given the value of the 2 which is in the residue. So 2, 12, 10 are considered as congruent of mod 10 and mapped to the value of 2. Next thing we have to understand is meaning of mod n. Whenever we are seeing mod n in congruent operation to the right side of the congruent operator, you have to see that it is a phrase. It is an indication of the distinction set Zn, destination set Zn. It indicates that the modulus is used in mapping. Please understand that when to the right side of the congruence operator, if we are using the mod n, then it is indicating that there is a mapping taking place between the integer set Z and residual set Zn. Please note that in congruence operator, mod n is not an operator. If you remember, in earlier modus arithmetic, when we used mod n, it was an operator indicating consideration of residue only. But here it is indicating the mapping between 2 sets Z and Zn. How it is going to happen? That we shall see it now. Now consider set of Zn, Z, which is being represented from minus infinity to plus infinity. Now we are interested in applying the mod 10 in congruence operation. And we applied this one on minus 8 mod 10, then 2 mod 10, 12 mod 10, and 22 mod 10. When we are using this one in the congruence operation, indicating that minus 8, I am talking that to the right side of the congruence operation, if we are getting minus 8, then mod 10, it is indicating that we are performing the mapping between Z and Z10. So mod 10 is indicating that we are interested in the set of residues between 0 to 9. So that is what is Z10. Now when I am applying minus 8 mod 10, the value which I am going to get is 2. This 2 is appearing in Z10, so we are mapping that value. Similarly, when I perform mod 10 congruence operation on 2, I get again 2. When I am doing it on 12, I get 2. When I am performing at 22, I get 2. Means when the congruence operation is carried out over many values, by considering the specific n value that we consider is 10, then in the residue set that we have created, the values will be from 0, then less than 10. Because of that, we are having 0, 1, 2, 3 up to 9 in Z10. Now we are working out the mod operations on different integer values in Z, which are mapping to one value. If you look at here, minus 8, then 2, 12, and 22, all are called as congruences. Since when we carry out mod 10 operation there, specific to that, all of them have given rise to a residue 2. Means set of integer values when are mapped by making use of mod of specific value, they result in mapping to the residual set. So this particular concept must be very clear to all of you, otherwise you struggle in understanding the next concepts. So residue classes. A residue class represented within square bracket A or square bracket AN is a set of integers congruent modulo n. Means we take a specific number, on that when we carry out a modulo n operator. When we carry out this, then we will get a specific value. For example, if you look at here, it is the set of all integers such that x is congruent of A mod n. Mod n is representing congruence operation here. Now, based on what is the value of n, we are going to get a number of residual classes here. Now if we consider the value of n as 5, then in the residual set we are going to have the values from 0 to 4. So there is one class 0, another class 1, another class 2, 3, 4. Now we are interested in picking up the values from the integer set z, which is giving rise to the value of 0. Now we go on looking at the values. For example, when I pick up minus 15 and apply the mod 5 on it, then I am going to get residue 0. Please remember, we are only interested in residues, not the quotient side. Similarly, minus 10, on that one, when I apply 5, once again I get 0 as a residue. Minus 5, 0. Then 0 mod 5 is 0. 5 mod 5 is also resulting in 0 residue. So like that, the residue class A, in this case residue class 0, is having the values which are giving rise to residue 0 when divided by 5 here. So the set is consisting of all those values. Similarly, the class 1, represented within the square bracket as 1, is considering all the values from the set of integers z, which are actually giving rise to residue 1. So minus 14 mod 5, it is giving rise to residue 1. Minus 9 mod 5, minus 4 mod 5, 1 mod 5, 1 the mod 6. Means here mod n, when I am referring, it is congruent operation. More specifically, what I want to say is minus 14 congruent of 5, minus 9 congruent of 5, minus 4 congruent of 5, 1 congruent of 5, 6 congruent of 1. All these things are giving rise to residue 1. Similarly, we can see that for residue 2, we have got when we perform congruent operation with n value as 5, then minus 13, minus 8, minus 3, 2 and 7 are giving rise to residual value 2. Similarly, for residue value of 3, using the modular congruent operation n equal to 5, then we will get the values like minus 12, minus 7, minus 2, 3 and 8. For class of residues 4, when we perform congruent operation with n equal to 5, then we will get minus 11, minus 6, minus 1, 4, 9. Means all these values are mapping to residue 4. Now we shall look at it how circular notation can be used to represent congruence. All congruent integers modulo n occupy the same point on the circle. Positive and negative integers from z are mapped to the circle in such a way that there is symmetry between them. Earlier we represented set of integers z which is moved from minus infinity to plus infinity. So that we are represented using a straight line. Minus n, minus 1, like that, minus 2, minus 1, 0, then it is moving towards the positive side, 1, 2, 3 and up to n minus 1. Now in congruence, which is set of residues, we are putting the circle. We mark here as 0. 0 is indicating the residue value. Now from the center point, when we will put the line, on that one, we are going to have all the values from the set of integer z that are resulting in zero value. Similarly, when you apply the congruence of Zn on the all values of integer set that which result in residue 1, then from the center of the circle up to 1, if we put a line, all the values that result in residue 1 will be coming on that line. Similarly, all the values of the integer set z that give rise to residue value 2 will be falling on the line starting from the center of the circle up to 2. Like that, we map all the values. So in case of Zn, the residual values will be from 0, 1, 2, 3, like that. They will be running up to n minus 1. Now we shall look at some of the useful properties of modulo n arithmetic. First property, a plus b mod n is a mod n plus b mod n, then congruent operation mod n. Second property, a minus b mod n equal to a mod n minus b mod n, then we are having congruent operation mod n. Third property, a into b mod n is a mod n multiplication of b mod n. It results in and mod n. So these are the three properties which are very useful in modulo arithmetic. Now we shall look at, these are called as algebraic structures. Means we make use of the basic set theory, we make use of modulo arithmetic, we make use of congruence, and using those basic concepts, we try to build higher algebraic structures. Because cryptography requires sets of integers and specific operations that are defined on those sets. The combination of the set and the operations that are applied to the elements of the set of numbers is called an algebraic structure. Means algebraic structure is a combination of set and the operations that are applied to the elements of the set of those numbers in that set. There are three common algebraic structures: groups, rings, and fields. Group, represented as capital Z, is a set of elements with a binary operation star, and it is represented as a pair within opening a caret bracket Z, comma star, closing bracket. Please note that this star is an operation, not a multiplication symbol here, in which the operator satisfies the four properties. One is closure, second one is associativity, third one is identity element, fourth one is inverse. What do you mean by closure? If A and B are elements of Z, the set G, then if we perform the operation star on A and B, whatever value is coming out of it, that also is an element of Z. If we take three elements A, B, and C, which are the elements of G, And when we carry out the operations as A star means operation A operation in the bracket, B operation C bracket complete, then we are going to get the result from carrying out the operation open bracket A and operation B bracket complete operation C. Then whatever values we get, A star open bracket B star C close bracket and A star B both bracket complete star C, when you compare it both will be equal. This is associativity. If it is happening, that is one of the properties of group. Third one is identity element. There exists an element I in G such that for all B in G, I star B equal to B star I. Fourth one is inverse. For each element B in G, there exists exactly one element in G such that element C in G fulfills B star C equal to C star B equal to I. C is referred to as the inverse of B here. So, in the set G, when we carry out the operation star, elements of G, if it is fulfilling closure property, associative property, identity element and inverse property, then that particular set is referred to as a group. Along with these four properties, if commutative property, which is indicating that for all A and B in G, if A star B equal to B star A, then we say that commutative property is fulfilled. If along with closure, associativity, identity element, inverse, if we see that commutative property is also being fulfilled, then we call that commutative group as commutative group. So to say a particular group and to say what is the category of it, these properties play a very crucial role. In case of ring, a ring is an algebraic structure with the two operations represented as open caret R, comma star, comma plus. If we want to qualify that particular set R is a ring, first operation star and second operation plus shall operate as follows. First operation must satisfy all five properties required for an abelian group, namely closures, associativity, identity element, inverse and commutative property, which we had seen in discussing group. Along with this fulfillment of first operations, second operation plus must satisfy only the closure and associative properties and must be distributed over the first. Means distributive means for all x, y and z elements of ring R, we have x plus within bracket y star z equal to within bracket x plus y star within bracket x plus z and within bracket x star y bracket complete plus z equal to opening bracket x plus z closing bracket star opening bracket y plus z and close bracket. When this is being fulfilled, then it is called as distributive. Means to qualify as a ring, the two operators star and plus must fulfill, and along with that there is a need for fulfillment of the second operation to be distributive. Along with these properties, if commutative property is also satisfied for the second operator plus, then we call it as a commutative ring. Now the last algebraic structure is field. A field F is an algebraic structure with the two operations represented as R star plus is commutative ring in which second operation satisfies closures associate with inverse and commutative property defined for first operation except that identity element of the first operator has no inverse. Means ring by nature it is commutative, the field by nature is commutative ring. Along with that, the one more condition is the identity element of the first operator shall not have any inverse. Except this, it has to fulfill remaining four properties. So with this, we come to the end of the session 4, and we shall consider some more examples in next session. And with this, we come to the end of the session 4. Today, we discuss about congruence. Congruence is mapping between a set of integer z with set of residue zn. It is representing equality, but in case of modulo arithmetic, we refer to as congruence. And we had seen that how we can represent congruence in a circular form. After that, we discuss on algebraic structures and group, field and ring concepts we had considered during the discussion. With this, we come to the end of the session. Thank you.